Welcome to the MIA course module on targeting lightning IDSS. This module focuses on how to use the latest tools and technologies and knowledge of storm environment to proactively predict lightning initiation, continuation, and cessation, rather than just reacting to the display of detected lightning. Here are the objectives for this module. It aims to help you understand the processes that lead to lightning initiation and cessation, to understand how new datasets, including the satellite day cloud phase RGB, dual pole radar field, and the MRMS -10 Celsius isothermal reflectivity, can be used to anticipate lightning initiation, assess threat continuation, and predict cessation. This course also aims to help you learn about the sources of error in these datasets that can hinder your ability to anticipate lightning initiation and cessation. Finally, to learn the process by which we can use the science to provide better lightning IDSS rather than just lightning detection via the NLDN. Hi, I'm Pete Wolf in Jacksonville, Florida. This is a fascinating module. I've long been frustrated over the reality that we provide service for every other hazard from severe thunderstorms, but for lightning, which kills or injures more people than the other hazards, and for which most people think is related to the severity of a storm, we do very little. The reality is that we just don't have the staffing to provide service for every thunderstorm affecting every town it tracks over. What we can do is provide IDSS for specific locations for specific periods of time, such as providing support to core partners dealing with outdoor events, such as concerts or sporting events. That's the focus of this module, providing science-based IDSS for this hazard. If you recall from the introductory module for this course, I differentiated between the recipe approach, which involved little science and was reactive in nature, and the science approach, in which we use science to be more proactive or predictive in nature. This applies very much so to the lightning hazard. Do we just track detected lightning, or do we use science to try to anticipate lightning initiation and cessation? In this module, you will learn about how to utilize the latest tools and technologies, such as our advanced satellite, dual pole radar, and MRMS, to accurately assess the threat. You'll learn about some of the issues associated with these technologies that lead to a probabilistic approach to threat assessment rather than a deterministic one. Our key goal here is to provide better decision support for core partners dealing with lightning threats at outdoor events, where large numbers of people gather. While lightning is a threat across the country, it is certainly a more frequent one across the southeastern United States, given a considerably longer period of the year with favorable conditions for thunderstorms. Likewise, the majority of reported injuries and fatalities occur across the southeastern U.S., but can occur anywhere. The key ingredient for lightning is not the rain produced by the storm or ice crystals at anvil level. It's the tiny balls of ice called graupel that develop at and above the -10 Celsius level within the updraft core. The collision of these different precipitation types yields different charges, with positive charges rising to the top of the storm and negative charges accumulating in the center of the storm. Positive charge can also build at storm base or at ground level. It is this separation of charge and attraction of opposite charges that lead to lightning. Predicting thunderstorms involves essentially the forecasting of tall enough cumulonimbus clouds to support graupel formation. For that, we need the storm core, which I'm defining as the 40 dBz reflectivity core, to reach above the -10 Celsius level. Low top convection with cores below this level generally don't produce lightning. Now keep in mind that I'm referring to the -10 Celsius level within the updraft core, which is close to the environmental -10 Celsius level in a very weakly unstable environment, as shown on this sounding, but can be thousands of feet higher than the environmental level in a moderately unstable environment, shown on this one. Predicting lightning initiation is fairly straightforward, with considerable accuracy, using radar and satellite to assess graupel formation in growing convective clouds. Predicting cessation of lightning is a bit more challenging. The National Lightning Detection Network, or NLDN, is our primary tool for detecting cloud-to-ground lightning, our verification, if you will. This is often used for event IDSS to alert officials of lightning within storms that are near or approaching the event area. This can be done by anyone, as it requires little science. As scientists, given the new technology available, can we do better? Consider a scenario where we have a band of intense convection with considerable lightning activity moving southeastward into an instability axis, with surface-based CAPE values above 3,000 joules per kilogram. For the Sioux City, Iowa area, marked by the arrows, what would you tell the safety manager for an outdoor event venue? Here are images at 2230Z, then 30 minutes later. How would you answer this question? Without any information to suggest the convective system will weaken, answer C would be the correct choice. This isn't very challenging, as one can just easily time the arrival of the thunderstorms moving toward the Sioux City area, likely arriving in the next 30 to 45 minute period. Try this question. Pause the video if you need more time. Key to effective lightning IDSS is the ability to anticipate the initiation of lightning as well as cessation, not just tracking detected lightning. So the correct answer is C. While NWP output is our primary tool for predicting lightning more than an hour in advance, within an hour we turn to satellite and radar as our key tools. Let's start with nowcasting lightning initiation, in which our focus is determining when we have graupel that collides with other particles, ultimately leading to charge separation, the immediate precursor to lightning. This module will not focus on thunderstorm forecasting specifically, as there's plenty of training modules within the CLC for that. A new NWP tool is the Convective Allowing Model, or CAM, that provides, among other fields, simulated reflectivity. Alone, this is not typically an accurate field, and results can differ from one CAM to another, and from one run to another of the same CAM. This can lead to confusing results. Instead, this field should be used with other fields focused on instability, shear, and lift. Consider a scenario focused on thunderstorm potential for eastern Ohio. Model guidance shows a strong shortwave, along with a surface front moving across Ohio, providing lift. A sample model sounding in eastern Ohio shows a very unstable environment. With instability and lift expected, more credibility can be given to the simulated reflectivity field from the HER model, showing the development of scattered thunderstorms over eastern Ohio, plus or minus an hour or so in terms of timing, as CAMs are frequently erroneous timing-wise. This information should lead to a yes answer to the question shown. We have two key tools from our new advanced GOES satellite, an RGB called Day Cloud Phase and the GOES Lightning Mapper, or GLM. Examples are shown to the right. The Day Cloud Phase RGB illustrates where lightning may soon occur by suggesting the development of ice particles within the cloud, as the colors change from blue to green to yellow. It is only available during the daytime, and can occasionally provide false alarms, where it may be suggesting ice crystals at the top of a developing cell rather than graupel. The GLM is a total lightning detector. It does not discriminate between in-cloud and cloud-to-ground lightning. It's simply a light detector, so it can overestimate the extent of lightning, such as where the light reflects off distant low clouds where lightning is not occurring. Try this question. Which is the correct answer? For a tropical cyclone, precipitation development around the core of the system is different than for extratropical system precipitation. Typically, we don't have the graupel to support lightning. Thus, the correct answer here is B. Now, that does not mean you cannot get intense convection that can produce lightning around tropical cyclones, particularly around the periphery of the storm. Here's an example from a 2020 tropical storm off the Florida East Coast, with the GLM showing lightning not only in the peripheral band of the north and west, but also with a blowup of deep intense convection just east of the center, as suggested by some 40 dB Z cores up to the minus 10 Celsius level on MRMS. So it can happen, and MRMS can be helpful for distinguishing cases when lightning may appear around tropical cyclones. Keep in mind that there are sources of error associated with these data sets. For one thing, for the RGB, the colors do not necessarily represent the same thing. The appearance of a yellow shade does not necessarily mean graupel has formed within the developing convective cell. Where GLM shows lightning is not necessarily where the lightning occurrence may be, such as when you have the light reflect off low clouds a considerable distance away from the lightning strike. On this example, note the lower clouds northeast and east of the convection on the top image, with the GLM suggesting lightning in these areas on the bottom image, despite no convective cell or anvil in those areas. You also have issues like parallax, which leads to a northward bias. Often you'll see NLDN strikes shown as white dashes on this image on the south side of the convective clouds on satellite as a result. The utility of radar for anticipating lightning has been known for a long time. There have been many research studies on this subject, including a larger one I completed and published in 2007 focused on the southeastern U.S. It should make sense that, given the processes that yield lightning, these studies should show a relationship between 40 dBz core height and the subsequent occurrence of lightning, usually with a 5 to 10 minute lead time for cloud-to-ground strikes. It should also make sense that the results are probabilistic, not deterministic in nature, due to the data issues that affect accuracy. A relationship is also seen between the height of the 40 dBz core, or, if you will, the depth of it above the -10°C level, and the extent of lightning that results. On these cross-sections, the left image is associated with no lightning, given that the storm core is below the -10°C level, around 8 kilometers. Greater lightning potential exists with the cross-sections further to the right. Taller cores generate a greater volume of charged particles, supporting a greater number of lightning strikes. This was seen in a 2008 study by Deerling and Peterson. Lightning jumps have been researched as a severe weather indicator, but they are usually the result of storm core jumps, if you will, which occur prior to the lightning jumps, thus with more lead time. Try this question. Pause the video if more time is needed. Remember that our focus is the -10°C level within the updraft core, so for positive buoyancy to exist, that level must be higher within the updraft than outside of the storm. For very unstable environments, the updraft -10°C level can be over 2 kilometers higher than the general environment -10°C level that the sounding shows. The correct answer here is B. From my study, a probabilistic relationship was found between the 40 dBz core height relative to the updraft -10°C level and the occurrence of cloud-to-ground lightning, as well as the amount of lightning produced. Probabilities for any cloud-to-ground lightning reached 50% as the 40 dBz echo approached the height of the updraft -10°C level, with probabilities maxing out as you get more than 5,000 feet above this level. For more frequent lightning, shown on the right column, say 1 or more strikes every 30 seconds, the probabilities reach 50% as the core gets to 10,000 feet above the -10°C level, and approach the maximum values as we got to at least 15,000 feet above that level. The storms that produced nearly continuous lightning typically had 40 dBz cores more than 20,000 feet above the -10°C level. Let me show you a few Northeast Florida examples where I replace 40 dBz core heights relative to the -10°C level with probability values from the prior table. As you go from scan to scan, note how probabilities rise to well above 50%, followed by cloud-to-ground lightning in white dashes 1 or 2 radar scans later. Note the 2 cells in northern St. Johns County where this occurs, as well as the new cell in northeastern Marion County. Here's another case example. We see several cells with rising probabilities leading to the occurrence of cloud-to-ground lightning with a short amount of lead time. Here's a case with several cells that have lower probabilities that do not exceed 50% and do not produce cloud-to-ground lightning. The only cell on this display that produced lightning was the one yielding greater than 70% probabilities in eastern Ben Hill County. Here's another example, comparing cells producing numerous to continuous cloud-to-ground strikes to a few cells over northeast Florida producing a lesser amount of lightning and showing lower probabilities. Note that the number in parentheses represents the probability for numerous strikes, which are maxed out for the southern Georgia storms. MRMS is a quick radar tool for assessing -10°C level isothermal reflectivity values. Here we see an animation with MRMS -10°C isothermal reflectivity on the left and GLM with NLDN output overlaid as white dashes on the right. Note the increase in reflectivities to at least 40 dBz shortly before lightning is detected. You'll also note the appearance of 50 dBz at -10°C level, suggesting the 40 dBz core extends well above the -10°C level, shortly before the appearance of a greater amount of 5-minute lightning activity. As with reflectivity cross-sections and all-tilt displays, MRMS can be helpful for differentiating between cells that will produce no lightning, like the far left image, and those that will produce isolated strikes and more numerous strikes as you look more to the right on this display. The problem with reflectivity displays, such as that with MRMS, is that the higher reflectivities could be grapple, or could be large raindrops, or a large quantity of small drops. For greater certainty as to the extent of grapple, dual pole products could be helpful. In particular, differential reflectivity can help discriminate between spherical targets and teardrop-shaped liquid targets. Here's an example that shows fields suggesting grapple above the freezing level, as indicated by the arrows, including differential reflectivity in the upper right with values near 1, and the HCA designation of grapple on the lower left image. Simply going with what radar shows can be problematic due to sources of error. For example, interpolation between elevation scans can affect how high the 40 dBz core is shown, including on MRMS displays. This can be really problematic a long distance from radars where the distance increases between the scans. Beam refraction can also lead to error in the height of radar detected features. If the top slice shown here hits the yellow 35 dBz area rather than storm top, possibly due to beam refraction, the interpolated 40 dBz height can be shown as higher in reality. In addition, the result can be influenced somewhat based on whether a radar is running warm or cool. MRMS can also be problematic, as it uses the environmental isothermal level rather than the updraft level. Thus, what is shown may not be representative in very unstable environments. These error sources suggest lightning prediction is better in a probabilistic framework than deterministic. So let's say we have lightning initiation. An LDN output offers no real forecast information. It's only providing past information about where lightning has occurred. How can we nowcast lightning threat continuation during the next 10 to 20 minute period using the new tools we have? In other words, how can we assess whether we continue to have conditions promoting charge buildup and separation? How would you answer this question? The only option that best relates to whether conditions are still in place to promote a continued lightning threat would be D, MRMS minus 10 Celsius isothermal reflectivity. Note that NLDN output only provides information on where lightning has occurred, not when and where it will occur. As long as the 40 dBz core is up to at least the minus 10 Celsius level, as seen either in single radar reflectivity cross-sections or all tilt displays, or MRMS minus 10 Celsius isothermal reflectivity, one can anticipate that lightning will continue until that's no longer the case. Would you answer this question true or false? Since charged particles may not be limited to just the main updraft core, the answer is false. Charged particles could be advected through an anvil, as shown on the right, or stratiform region of a convective system as shown on the left, leading to lightning a considerable distance from the storm core. Let's turn to the more challenging topic of anticipating lightning cessation. And for this, we're not focusing on silly rules of thumb like the 30-30 rule. Instead, we'll focus on using science to try to understand when we no longer have conditions for charge separation within a convective cell, or within a storm anvil or stratiform region. So the threat of lightning continues until there is no longer particle separation resulting from ice and liquid particle collisions within the updraft core. In weak flow storms with very short anvils, the lightning threat likely ends 10 to perhaps 20 minutes after the storm weakens, possibly sooner at times, as the setup of charge separation diminishes. In stronger shear environments, with more extensive anvils or large stratiform regions of convective systems resulting from a front-to-rear flow structure, the threat of lightning can continue for some period of time after the main convective cells weaken. The advection of charged particles through the anvil or stratiform region can promote lightning strikes a long distance from the original storm cores, with the threat lasting until the charged particles diminish within these features. How would you answer this question? Pause the video if you need more time. Since both A and B are correct, the correct choice would be answer D. For the storm cores themselves, you need for them to weaken such that the 40 dBz core no longer reaches the updraft minus 10 Celsius level. And even then, it may take 10 or 20 minutes for the charged particles to disappear or fall out of the core. For storms or systems that have long anvils or stratiform regions, there needs to be a disruption, such as breaks in the precipitation field, or a sufficient time to pass for the charged particles to dissipate or descend, thus having no further separation of opposite charges that would promote lightning. Here's an example of a storm in far northwest Georgia with a 40 to 50 dBz core up to at least minus 10 Celsius, producing lightning as shown on the GLM product. It's the northern storm. Over time, the core weakens, thus suggesting the end of the lightning threat. However, there is an anvil extending southward, where the threat may continue, at least until one observes breaks in the 20 plus dBz reflectivity, represented by the green color, which happens fairly quickly in this example. Here is an example across northern Missouri. A line of storms moves southward, with good cores still seen on this MRMS image along the southern periphery of the precipitation field. The cores are still likely advecting charged particles northward in the front to rear flow pattern aloft through the stratiform region, where lightning continues to be detected as shown in the GLM product. So unfortunately, anticipating cessation is not as simple as just waiting for the 40 dBz core to drop below the minus 10 Celsius level, and yet we can provide much better information than the unscientific 30-30 rule. Okay, let's wrap up this module by having you try a few exercises. This first exercise will be providing lightning IDSS for an outdoor event in Fort Smith, Arkansas. A line of thunderstorms moved southward across Oklahoma and western Arkansas. Radar shows a large stratiform precipitation region in its wake, extending across eastern Oklahoma and western Arkansas. As the IDSS person, you're providing support to the security staff for a morning outdoor event in Fort Smith. They are reporting occasional lightning flashes and rumbles of thunder and want to know when the threat of lightning will end within 5 miles of the event area, which is marked with an X on the images. Think about what you would brief them at this point. With the stratiform precipitation still connected to the tall storm cores, the threat of lightning is likely to continue for a considerable period of time, potentially an hour or longer. The time frame would be much less if the main storm cores had diminished, but as they're still going strong, the threat will likely continue for at least another hour. Okay, 30 minutes have passed. Look at this imagery. Security officials still report occasional lightning and rumbles of thunder. They ask when you think the threat will end for the event location. What would you say at this point? We still see the stratiform region extending across southern Oklahoma into southwest Arkansas, which is mainly south of the event location. The convection producing this precipitation has weakened considerably. There's new convection further west producing its own stratiform region over south central Oklahoma, but that is not a factor for our event. For the Fort Smith area, it still may take another 20 or 30 minutes for any charged particles to work through the stratiform region and diminish or descend before the lightning threat truly ends. Watch how the imagery changes over the next 30-minute period. With loss of charged particles within the stratiform region across southeast Oklahoma, the lightning threat appears to have ended. In particular, there is no 30 dBz echo anywhere near the event area, so I would not expect lightning to suddenly reappear. We see lightning activity in the stratiform area over south central Oklahoma, resulting from cores along the Oklahoma-Texas border. Your next case will cover 2 cells in northeast Florida. You are providing support for security staff at 2 outdoor events, one in downtown Jacksonville, marked with an X, and another on the southern end of Amelia Island, marked with a Y. They don't care about rain, they're interested in the lightning threat within 5 miles of event locations. We have a moderately unstable environment with a sea breeze moving inland as the main source of convective initiation. It is 6 p.m. What would you brief these officials on lightning potential? Using just a day cloud phase RGB, with some green and yellow shades, in a favorable environment, you might suggest lightning potential during the next 20 to 30 minute period over downtown Jacksonville and with a developing cell west of Amelia Island that could affect Amelia Island beyond 30 minutes out. 15 minutes have passed. Here we see the RGB images on the left and the MRMS -10 Celsius isothermal reflectivity images on the right. How might you update your briefing information on lightning potential? These images continue to show potential for lightning. Is that threat imminent? Possibly for the downtown Jacksonville cell, given the appearance of 40 dBz echo right at the -10 Celsius level. Keep in mind that you're looking at the environmental -10 Celsius level, not the updraft level. 5 minutes later, are there any changes needed to your briefing information? We see a larger 40 dBz core at -10 Celsius around downtown Jacksonville to suggest that lightning, which has not yet been detected, is imminent around downtown Jacksonville. No sign yet of an imminent threat for the cell west of the southern end of Amelia Island. Another 10 minutes have passed. Still no lightning detected with these cells. Do you back off on lightning potential? No. In fact, I would suggest lightning appears quite likely at both locations during the next 10 to 15 minute period. You could use dual pole to try to confirm Grapple above the freezing level, but the data shown here alone strongly suggests high potential for lightning, especially for the downtown Jacksonville cell. Here we see the next two 5-minute images showing detected in-cloud lightning for both cells. Shortly after these images, NLDN shows a few cloud-to-ground strikes for both storms as indicated by the white dashes. For the storm now southwest of Amelia Island, note the isolated cloud-to-ground strikes likely within the Anvil region passing just south of the island. Even if the storm is not within range of an event location, one must monitor possible Anvil regions or stratiform regions of convective systems that could pose a lightning threat. The third and final exercise will cover an outdoor event in Burnsville, Minnesota, a town located to the south of Minneapolis. As the IDSS person, you're providing support to the security staff for an outdoor event in the suburb of Burnsville, marked by an X on the right image. They see clouds building and they need to know when lightning is imminent within 5 miles of event location. Rain is not a big deal here, but lightning is. Based on the last 10 minutes of RGB and GLM data and MRMS -10 Celsius isothermal reflectivity data below, and an environment that is marginally favorable for thunderstorms due to marginal CAPE, what would your briefing be for security staff about lightning potential over the next 30 to 60 minute period? Given what the RGB and MRMS images show, you would likely lean toward a possible threat during the next 30 minutes, though potentially not imminent given the distance of the cells from Burnsville. 10 minutes have passed. We have some building cells on the western flank west-southwest of Burnsville, moving to the east. Would you change your briefing now? Again, there are indications of possible, but not necessarily imminent lightning. Though not included in this exercise, one could look at dual pole to see if Grapple is shown above the freezing level, thus influencing your expectations. Another 10 minutes have passed. Still no lightning detected. Any changes to your briefing? Once again, the data suggests potential lightning, but not necessarily imminent lightning. Without the use of dual pole data, we cannot discount the potential for Grapple being indicated by both images. From a probabilistic perspective, with 40 dBz echo getting just to the -10 Celsius level, probabilities are likely getting to around 50%. Yet another 10 minutes have passed. Once again, are there any changes you would make to your briefing? It's not looking good for lightning right now. While we see the yellow shade and some texture suggesting good cores on the RGB image, we're just not seeing any decent 40 dBz cores up to and above the -10 Celsius level on the MRMS display. So probably no changes. Possible, but not necessarily imminent. This was a more challenging case. No cloud to ground or in-cloud lightning was detected within this cluster of showers passing south of Minneapolis. The cores likely consisted of supercooled water drops rather than Grapple. While the MRMS suggested 40 dBz echo getting to the -10 Celsius level, MRMS uses the environmental, not the updraft, -10°C level. Dual pole data might have been helpful in suggesting no grapple detected, thus no imminent threat of lightning for this event. Here's a summary of key points from this module. By understanding the processes that lead to lightning initiation and cessation, we can use the latest technology to provide useful event IDSS support. NLDN provides detection of only cloud-to-ground lightning, while GLM provides in-cloud lightning as well, which can provide some lead time ahead of cloud-to-ground strikes. Unlike utilizing just NLDN for tracking existing lightning, satellite and radar can be utilized to nowcast lightning initiation, continuation, and cessation. Satellite provides tools like the day cloud phase RGB and the GLM, but they can have potential error leading to misinterpretation of lightning threat. Radar provides tools like dual pole fields and MRMS -10°C isothermal reflectivity for detecting grapple, leading to separation of charges, a precursor to lightning, but these datasets also can contain error. You have reached the end of this module. Please complete the following learning assessment. It is not graded, it's just provided for your benefit. Pause the video as needed and write down your answers. Question slides will be immediately followed by answer slides. If you missed 2 or more questions from this assessment, you are encouraged to review the module again and retake the assessment, and discuss anything that may be confusing to you with your local training program leader. Good luck.